Welcome, everyone. So we're going to start the panel discussion. We're going to talk about solar system, solar Earth-based space and ground observations of Proxima Centauri b and other planets around nearby stars. So we have a great panel, and we're going to sort of take over from what we heard this morning and go more in-depth into discussing how we observe planets to find biosignatures, what we should be looking for, and discuss life on nearby planets. So I'll let the panelists introduce themselves briefly. Dave?
Okay, so I'm Dave Charbonneau. I'm a professor of astronomy at Harvard, and I'm very interested in transits and mass measurements and opportunities to characterize small rocky planets orbiting nearby stars. I PI the MERTH project, which announced the discovery of LHS 1140, which we heard about this morning. We announced that yesterday. And I'm involved in the Kepler and the TESS missions and so on.
Thank you, Dave.
My name is Kaltenegger. I'm the director of the Carl Sagan Institute at Cornell. I'm really interested in the question of searching for life inside the solar system and using that information to actually inform our search outside the solar system. And I have an interdisciplinary team to do that at Cornell, and I'm also involved in TESS, in James Webb Space Telescope. And I'm really kind of agnostic to how we're going to get these features. So I like all wavelengths and like all telescopes. So I'm just trying to make this work.
Hi, I'm Nikole Lewis. I'm an astronomer at the Space Telescope Science Institute, where I also serve as the JWST project scientist. My research usually involves anything that will characterize the atmospheres of exoplanets of all sizes, and I'm especially interested in doing that with space-based facilities like Hubble and JWST.
My name is Mike Meyer. I'm a professor of astronomy at the University of Michigan, and I started my career in star and planet formation and increasingly have moved towards exoplanet discovery and characterization primarily through direct detection and direct imaging. And so I'm excited to hear about the prospects and talk about the prospects of imaging these very, very nearest planets with the very, very largest ground and space-based telescopes.
Hi, my name is Dimitar Sasselov, and I'm a professor of astronomy at Harvard with background in stellar physics, then got excited about exoplanets and theoretical modeling and characterization studies of those. And then about 10 years ago, got even more excited about the chemistry of life and how it could emerge under planetary conditions. Hence, I've been the founding director of the Harvard Origins of Life initiative now for 10 years, and the newer Simon's collaboration on Origins of Life, which connects chemists, biologists, and planetary scientists and astronomers.
Thank you. So for the next 35 minutes, you're going to hear us ask each other questions and hopefully answer them. The 35 minutes after that, you will have opportunities to ask questions. So you can already think about trick questions, and hopefully we can answer them. So I'm going to start with you, Dave. It seems like M stars keep giving. There is planets everywhere on M stars. When will it stop? Have we found most of them? What's next?
Yeah, so I think a really important thing to remember is we have not searched most of the nearby M dwarfs. I would advocate that we have to do a transit survey of all the M stars within 15 parsecs. That 15 parsec number comes from a variety of considerations. The first is using the statistical results from the Kepler mission. We know that within 15 parsecs, we'll have several transiting temperate rocky planets. So that gives us a critical number to actually go and study their atmospheres and so on. The other issue is that beyond 15 parsecs, the prospects for studying these atmospheres with James Webb, which we'll hear about, and the upcoming EELTs basically moves out of view, that the inverse square law just kills us. So that's the volume of space that we have to do a complete survey of. We were delighted to announce LHS 1140. If you ask how many of the nearby M dwarfs did we have a comparable data set at the point at which we detected the planet in that data set, it was only a tiny fraction of these nearby M dwarfs. So most of them have never been looked. And similarly, we have to do an RV survey. Now, the RV survey, you may not have to go out to 15 parsecs. If you want to study planets in transit, you have to go out to 15 parsecs. If you want to do imaging since you don't need that special geometry, you're probably happy going out to, say, 7 parsecs or so. But again, that's not been done. Most of the M dwarfs out to 7 parsecs have not been studied, monitored with radial velocities. And so there are many, many more planets to find.
So I'm very curious. I don't know if anyone has looked at the numbers, but given the recent discoveries around especially late type M stars, what is, and the fact that transits are essentially a low probability event, what is, I mean, we've heard there's maybe 2.5 planets, rocky planets per star, per M-type star. What's your guess?
Well, so if you take Courtney Dressing's statistics as part of your thesis work, Courtney, you're in what's really exciting is in Courtney's paper, she said the closest transiting habitable zone rocky planet around an M dwarf should be 10.5 parsecs away. And TRAPPIST-1 is 12 parsecs, and LHS 1140 is 12 parsecs. So that's a pretty good prediction. But if you look at, which is what I was alluding to, if you look at the number of stars that TRAPPIST looked at by the time they found TRAPPIST-1, if you look at the number of stars we looked at before we found LHS 1140, we seem to each hit pay dirt a little early. So that might indicate, it's just small number statistics, but it might indicate that the rate of occurrence is actually higher. So if the rate of occurrence were 100%, then the closest transiting one might be only 8 or 9 parsecs away. And compared to 12 parsecs and an inverse square law, that's a huge benefit to us.
That also means that, well, we also have another point, which is of course the closest star to us does have a planet.
Right, and those three together sort of indicate, you know, maybe the rate of occurrence is even higher.
So I want to spend the rest of the time focusing more on what's more exciting to me is biomarkers, finding them, and life, detection of life. So Nikole, NASA has some pretty exciting missions coming up that will get us on that path. Can you tell us a little bit more about JWST and also how it plays with TESS?
Yeah, so 2018 is going to be a really busy year for exoplanets because we're going to launch both TESS and JWST within a few months of each other. TESS is really exciting because we get this whole sky survey looking for planets transiting nearby bright stars. So we're going to get great statistics. It's going to further inform a lot of what Dave was already talking about. But we're also going to find a lot of planets nearby with TESS that are prime targets for atmospheric characterization studies. And with the launch of JWST, we'll have access for the first time to the 0.6 to 28.5 micron wavelength range from space, using 4 different instruments, providing a huge range of basically imaging and spectroscopy modes. So we'll have ample opportunities to study, planets like LHS 1140b, TRAPPIST-1, and others that are discovered with TESS in just the near term.
Can you tell us a little bit more about how the observation is going to happen? How many transits do you need? What molecules are you hoping to detect?
Right, so the great thing about the sort of infrared is it's littered with molecular signatures. Water, methane, ozone are some of the key ones that we'll of course be looking for in terms of biosignatures. And they're accessible through a wide range of different modes on JWST. So we'll begin looking for those as soon as it gets up there using mostly transmission spectroscopy. So again, this is where the planet passes in front of the host star and the starlight is filtered through the planet's atmosphere and you get that imprint of those molecular signatures on that stellar signal.
Great. I can't wait for JWST to launch.
Yeah, neither can I.
Michael, let's talk about what we can do from the ground with imaging. So there are larger telescopes being built. We already have fairly large telescopes. What can we do, and especially can we do something on Proxima Centauri B?
Well, I guess I'm a little more optimistic than the way Marcus presented his lovely talk earlier today. In particular for Proxima B, it's hard. The planets are very, very, very close to their hosts. And so it may be we have to use a slightly more exotic technology like nulling interferometry to really make a go of it. And just working the numbers out on the back of an envelope, in principle, you would have the angular resolution at 0.5 lambda over d to get access to the thermal emission at 10 microns from something like a VLTI, if there were an instrument prepared to take advantage of that baseline, or I've even speculated, and will horrify some members of the collaboration in the audience, but there is a tunnel between the Magellan telescopes on Las Campanas. And a 60-meter baseline would be lovely for exactly that observation, to get you right at 0.5 lambda over d. So in principle, it's doable, but it's a very, very hard observation to make.
So let's talk about what EELTs will do specifically, because they are going to have a combination of the type of baseline, sort of 30-meter-ish aperture you're referring to, and greatly improved sensitivity.
Yeah, so in the future, that same kind of observation could be done on 2 elements of a GMT telescope, for example, used as a nuller, or the EELT, just at the edge of observability, just at sort of 1 lambda over d. Having that access to the larger aperture allows you to take a few steps farther out, and sort of alluding to what David was talking about, if you just roll the dice based on what you know Kepler has already found as a function of planet size, as a function of stellar host, as a function of orbital radius, you extrapolate a bit and then predict what you might be able to see. And there ought to be a trove of, up to a dozen planets that one could, in principle, directly image very close to their host star. Now, these would be planets that would be in thermal equilibrium with their star, so you don't have to worry about the cooling of the planet, which would plague the search for outer gas giants at those nearby star ages, which are very old, as we talked about earlier today. So that makes that difficult. But an equilibrium temperature within an AU or so, it just expands the volume out to 5, 6, 7 parsecs, where you have a hope to get some good observations. I should clarify, I'm not only talking about planets in the habitable zone, where liquid water could obtain on the surface in equilibrium, but hotter planets, which turn out to be slightly easier to detect. So in principle, in the 3 and 5 micron band, you could also detect handfuls of planets, again, rolling the Kepler statistics and just hoping for the best.
So I want to bring you back to habitable planets, the only ones I'm really interested in. We've talked a lot about M stars, but you've been working in thermal infrared, longer wavelength instrumentation for the ground, which is a little more suitable for hotter stars. So do you want to explain how that plays and why we should not forget about sun-like stars?
Well, it used to be that if people talked about ELTs and imaging planets in the habitable zone, they were only talking about reflected light. And then it was very clear you had to do that for around M dwarfs, because those planets were going to be very close, and you didn't pay this 1 over r squared penalty in the reflected light at very large radii. But in the thermal infrared, it turns out it's easier to image a planet in the habitable zone around FGK stars, where you push that boundary out a little bit, and then you have a little bit more angular separation to play with in terms of doing the resolution. So for the thermal infrared imaging, it's the FGK star sample that will be easier to access the habitable zone. In reflected light, which I would think would be the 2nd generation of habitable zone planet imaging, you definitely would want to go for the M dwarfs. And ultimately, as we were talking about at lunch, you want both, of course. You have to be able to image in thermal emission and in reflected light to resolve the albedo radius ambiguity. And then you can just imagine starting to look for things like greenhouse effect. If you know the insolation and you know the albedo and you see what the thermal emission is, you can start to disentangle the system for real.
One thing I like about the sun-like stars is, as opposed to the M dwarfs we hear about, which have completely opaque, mysterious names, you can name them, and they're bright stars in the star. So maybe you can name what are your top targets.
Yeah, well, Altair, Procyon, Sirius, Alpha Centauri A and B, for example, are among the great targets.
Those are mostly hotter stars you're naming.
That's true, and I'm just saying if you roll the dice, they're not in fact sun-like stars. Well, Procyon, F, but Sirius certainly is, and Altair. The challenge there is to, they're very bright stars, and it's a relatively limited sample. But indeed, it helps a lot to be able to image in the thermal infrared at slightly larger angular separations.
So I want to go back to actually transit.
I'm sorry, something I wanted to mention is that many of those stars are multiple star systems, and that is quite an important thing to take into account. It may not be that easy to get the habitable planets in the right place around a binary star system, and we've already seen some evidence with Kepler that those frequency of smaller planets goes down when there are binaries within, say, 50 AU. And so that's something important to take into account.
That's actually a very important point, because, well, you know which stars I'm talking about. What does a white dwarf having a white dwarf around you do to your chances of having habitable planets?
Well, I'm not an expert in the dynamics of each of these systems, but I do know that there is still room dynamically, and if Jack Lissauer were here, he could help address that. Certainly for Alpha Centauri and B, there's room to look, so we're happy for that. But you're absolutely right. In terms of Sirius and some of the other systems, we have to think carefully about what, even if we can access it, what are the probabilities of having something stable in those places?
We talked this morning about the danger of having an active star in the early days of the planet. Sirius is an extreme example of this because the Sirius B is a white dwarf. It was a large star that went white dwarf in a fairly unfriendly process for the planets.
Yeah, that may not be the best place to look first.
So I want to go back to transit spectroscopy. So questions for Dave and Nikole, and I want to poke a little more at what is the complementarity between ground and space in terms of transit characterization. So maybe Dave, you can start and give us your thoughts about that.
Well, we were talking about this. I think that you really need both. My understanding, my takeaway from the talks this morning was that most, arguably all, cases for inferring the presence of life through the study of gases in the atmosphere of a planet involve oxygen, molecular oxygen. Now, that's not uniquely true. There are cases of perhaps looking at methane and other carbon compounds. So you really do need that ground-based work because although James Webb does nominally have sensitivity at O2 wavelengths, combined with a small aperture of the telescope, you probably can't get there. So I think what will happen is hopefully with the Giant Magellan Telescope or the EELT, the combination of all of them, we will be in the position of having detected molecular oxygen. But if we only have that, we can't interpret it. And it's hard to really do any other molecules from the ground. So of course, what you need is some way to access all those other wonderful molecules that have all the spectroscopic activity in the infrared. Water, methane, CO2, to put that oxygen in context. And of course, that's what James Webb will do. So my vision here is we have to find these closest transiting planets. Maybe we have already found them with TRAPPIST-1 and 1140 and so on. Maybe there's some better ones. Over the next 3 or 4 years, we'll study them with James Webb and characterize all those various molecules. And then with the EELTs, then we'll go and detect oxygen. And then together with one final thing, which is we have to get the UV spectra of those stars with HST before it decides to finally retire, then we could actually maybe put that molecular oxygen in context.
Can you mention briefly why we need the UV measurement? Why is it important?
Sure. I think like, let's say there's a very exciting detection of ozone with JWST, which is possible. I think any of the theorists here would be hard-pressed to interpret that ozone if they didn't know what the impinging ultraviolet radiation was on the planet. And HST is really the only facility that can deliver that ultraviolet spectrum. And of course, it could break and stop working at any time. So of course, the chemistry in the atmosphere, particularly the upper atmosphere and things like ozone, is very affected by the impinging UV flux.
Isn't the UV flux something we know from basic stellar physics, or do we actually need additional measurements?
If you go into the HST archive and you say, how many, surely, before we found planets and there was nothing interesting to do, surely they used HST to get the UV spectra of all the nearby stars, but that is not true. We actually don't have the ultraviolet spectra of even 5, 10 of the closest M dwarfs. We have here or there, we might have something for Proxima. So it's astounding how little we know about the ultraviolet emission of these nearby M dwarfs. So
I'm used to optical and near infrared, and the spectra is just a function of temperature. I hear that it doesn't hold in UV.
Not for the cool stars.
Right. So the ultraviolet emission is not Planck emission. That's the fundamental difference, right? So it absolutely does not. And I think there's a lot of exciting work being done right now to understand, are there things you can measure about an M dwarf that will reliably predict the UV? So for example, if you measure the spin rate of the star, is that enough to predict the UV? The spin rate and the mass, is that enough? Spin rate, mass, and maybe something easy like H alpha, is that enough? So if we can build up those relationships, even after HST has stopped working, we'll probably be able to make an informed guess for interpreting the spectra of a planet transiting some other M dwarf. But all of that hinges on getting those UV spectra now so that we can build those relationships. And so I think it is a really, really important program.
Yeah. So if I can just add to that, I mean, having broad wavelength coverage gives you a full picture of the entire planetary atmosphere from, the exosphere all the way down to as close as you can get to the surface, at least. And in addition to just learning more about the stars, there's, of course, the hope of trying to detect exospheres of these rocky planets in the ultraviolet with Hubble. And if we understand escape rates from these nearby rocky planets, it's going to put a lot of answer a lot of important questions, which everyone's always been asking, like, what is the escape rate? Can they retain an atmosphere? If you can actually measure those hydrogen molecules in particular escaping, we'll be able to answer those questions. And it's something that only Hubble can do.
Nikole, I'm very interested in the story behind JWST becoming a sort of exoplanet characterization machine. The project has been going on for a long time, and at the beginning it wasn't one of the primary science goals. How did that happen, and how much did the team have to change instruments to make this happen?
I guess I'll answer, and maybe Mike can chime in later. All I can say is thank God for delays. If JWST had launched when it was intended to launch, we would not have the capabilities for doing exoplanet characterization that we have today. And it is the first mission where, unlike Spitzer and Hubble, these space-based missions that do characterization of exoplanets, they were launched before we really even knew exoplanets were a thing, whereas we have this rare opportunity with JWST where we know that there are tons of exoplanets that are just waiting to be studied. Now, the great thing that we learned with HST and Spitzer in particular is that you don't actually have to change the instrumentation that much in order to achieve your science goals in terms of high precision time series, spectroscopy, and photometry. So there are modes on JWST in particular, the nearest sauce mode, as it's called, that's been specifically designed to do these transmission spectroscopy studies. But for a lot of the other instruments, it was just making simple accommodations for doing these long duration time series observations of bright objects.
Maybe it's a good time to mention the Spitzer story, especially the warm Spitzer mission. So maybe you can tell that story to the audience.
There's so many stories from warm Spitzer, I guess. I cut my teeth on warm Spitzer, but it's been a workhorse for both studying exoplanet atmospheres and, of course, detecting systems, the additional planets in the TRAPPIST-1 system, which is the recent news, which I think you're alluding to. Spitzer is able to provide incredibly stable, long baseline photometric observations. I love Hubble, but the fact that it's orbiting the Earth is a pain. Spitzer allows us to stare at things for, say, 20 days at a time in order to characterize these systems further and detect additional planets.
And originally, Spitzer was supposed to not be running right now. Right? It's an infrared telescope. It needs cooling, and it's doing something very exciting right now. Even though it's not cool anymore. So maybe you can explain that.
So it was actually really great for us in exoplanet science to have Spitzer have these two wavelength bands still accessible. It's the 3.6 and 4.5 micron channels. It happened to align perfectly with the peak of thermal emission from hot Jupiters and other planets. And that's where a lot of this field started, including the early work by Dave and others in 2002, was to use Spitzer to look for thermal emission of exoplanets. And that's a legacy that JWST will carry along as well. And folks have actually posited using JWST to look for thermal emission of planets like Proxima b.
So let's move more into the life finding and life on exoplanets. The first thing is when we think about characterizing the planet, we must think about the whole system and the context behind the formation and evolution of the planet. So, Mike, you've been advocating for us to have this broader vision of planet formation and especially impact of other planets on inner planets. Can you tell us a little bit more about that? And I think you brought something that you want to show us as well.
I did. It's not much. It's about all I could afford from the Tucson Gem and Mineral Show. But this is a pallasite, a little chunk of a meteorite, which I have. And it's a mixture of fully differentiated material, an iron agglomeration, and some olivine, some SiO4 green crystals, which you can see in there. And it's beautiful, so I like it very much. But it reminds us that early planet formation is a knock-up. It's really a messy business, and giant impacts are part of our classical canonical story of terrestrial planet formation. And 10 years ago, part of our story for how the water on the Earth got delivered to the Earth was through the Jupiter and Saturn, or Jupiter in particular, throwing things in of icy bodies from out beyond the ice line that could bring that water and lead us to the D to H ratio of the oceans that we have. There is a much more complicated part of that story, but, and some of it I'm on both sides of, and Dimitar can chime in here too, because he's worked a lot on this. But the question about the global architecture and whether you need gas giants beyond in order to have a habitable planetary system, I think is an interesting one. And in particular, because of this dependence of the frequency of gas giants on host star mass, which I think is now fairly well established, it brings the M dwarf versus FGK star story into somewhat more complicated terrain. That's all I wanted to raise with that.
Maybe you can give us a brief history of the 4.5 billion years of history of that piece of rock you just
Well, this one was probably made within the first tens of millions of years of the solar system, and then it was quietly sequestered in the asteroid belt. Well, there's still controversies on how pallasites form, but a modern theory championed by colleagues at the University of Hawaii is that it's leftover differentiated material and undifferentiated material, which came together as an amalgam and then existed as a parent body in the asteroid belt until a piece of it was knocked off and delivered into an Earth-crossing orbit, and there we have it. So the interesting bit was the first tens of millions of years when the heavy giant impacts.
And this is not your usual rock. It looks a little different than a normal rock. Can you describe what people... Actually, sorry, I'm putting you on the spot. If it's not too valuable, maybe you can pass it in the audience and they can have a look for themselves.
Well, if it disappears, I'll send you a bill for $300 or something like that. It's not that valuable, but the green olivines are an interesting silicon rock, which is commonly found on the Earth, and different amounts of magnesium and other trace elements are incorporated into those rocks. And please speak up, geochemists in the audience who know more about these rocks than I do. And it's mixed, very intertwined with the iron, which is presumably from a more fully differentiated body. There are some isotopic evidences that the parent body that was differentiated had to be more than 80% fully molten in order for some of the chemical signatures to be obtained in the rock.
So let's talk about biosignatures. So Lisa, you've been giving this a lot of thought. I happen to design instruments. What should I be looking for? What biomarkers are most essential in spectra, mass? What do we need to know about the planets, and what do we need to measure?
I think the key thing about this is that we're starting out being extremely conservative, because there's a wide range of what we could be looking for that indicates life. And when you have a look at the Earth through its history, and this is not just the first 10 million years when it starts to get interesting for life, the biosignatures changed, and that was David's talk. He showed the difference in chemicals in our atmosphere, in our air. And I usually use that when I teach. I say to my students, if anybody ever invented a time machine, the one thing you need to bring is a gas mask. Because you open the time machine and you're dead, because you can breathe the air of an early Earth. And that usually seems to stick with them. But that also tells you that we have a range of things to look for. And I completely agree with Nikole and David, the more information, the better. But if you actually have to narrow it down, and I think this was also what David was showing us, we have these priors and so on and so forth. We have one data point for life. That's our own planet. And so for now, we'll use what we know from the Earth. If we get a second data point, what I hope we do, I think all our priors are going to change, and we're going to have a huge variety we can look for. But for now, taking Earth's life, you would want to have a combination, and David alluded to that, from oxygen, but not alone, but with a reduced gas. And just because that would tell you that it didn't build up slowly with nothing to react with, but that something actually produced it in huge amounts.
So oxygen and methane, for example?
Oxygen and methane, or ozone and methane, it really doesn't matter in a way. So David made a really good point that you would want to have the oxygen to try to constrain the full amount of how much oxygen is in the atmosphere. However, if you only had the ozone marker that traces that there's oxygen there, it's in a way actually a better marker because it's saturated, so that the line is incredibly big initially. So you can't really say how much oxygen you have, but you see it easier than the oxygen feature in the visible. So I think if you If you put me on the spot, I would say oxygen with reduced gas, and for our own Earth, methane is the one you would see. So oxygen and methane. And the great view, and this is where we come back to breakthrough, is actually that the methane actually starts to build up for cool stars. So this combination that's actually pretty tricky on the Earth becomes much better if your star becomes cooler. And then we have talked about the real importance of the activity of a star, because the activity of a star, of course, changes the photochemistry in the atmosphere. But even if you run this for the most active star that you know versus the most inactive star that you know, you still have the combination of oxygen and methane, or ozone and methane, really, because the problem is there's not much flux in the visible for an M star. So if you don't have a transit but an emergent flux, it's really hard to see an oxygen because there's just no light. In a transit, it's a little bit better. But so if you wanted to build me an instrument currently, I would say make sure that you see ozone and methane or oxygen and methane. And then it depends which wavelength range you're at. But one of the other things I want to throw out, because this is the breakthrough discussion, right? So we have been very conservative, and we are, about doing life on this Earth and using this. And this is what we should do. This is the scientific basis. And I know that Avi asked about life as we don't know it. But however, even life as we know it, like this, for example, there's Jax in the audience, one of our postdocs. We just had a paper out in this UV environment where the UV flares and basically could sterilize the surface of a planet like for Proxima b. If you had planet sheltered below water or the surface or just dirt, life would be fine. Life could start to evolve. The question is, when it goes down, it's harder and harder to detect. However, there are some coping mechanisms for the UV flux even here on the Earth, and this is where we get into breakthrough territory, because they are corals. When you hit them with a lot of UV flux, they start to biofluoresce because they live in symbiosis with an algae that can't deal with UV radiation. So it is life as we know it. But you could actually imagine, and this is an imagination a bit further out, you have the star, it actually starts to flare, the UV flare hits your planet, and this planet actually lights up in the visible wavelengths, not due to reflection, but due to breaking down the UV, the additional UV flux. And I just like this idea because we need to think a little bit outside of the box, and I think Courtney's and Amawa's talks were great, where these red suns might just allow us, what we found is that there's a very different kind of planets we could find there, and it's just take the TRAPPIST-1 and LHS, right? So there's probably a huge diversity. So thinking just a little bit outside of the box of what you should be looking for, what might not be a biosignature that you think about for the Earth, I think is definitely something we should do. And not worrying about us standing on the surface. I think that was Avi was alluding to, is like, even if you don't have a moon, right? If life evolved in an ocean, it's going to be fine. It doesn't care what the surface temperature is. And if it wants to go to the surface, if it has a weird surface temperature fluctuation, it will evolve for it or will die. That's evolution, right? If it starts on another planet, that's the huge open question. But looking as far as humanly possible, I think, will give us the best.
So let's talk a little more about origins of life. Dimitar, you actually are heading an initiative, a collaboration between astronomers and people who study origins of life on Earth. Can you tell us a little bit more about this?
Well, it is an important question because I think ultimately we'll have to confront it in other ways than what the collaboration is doing now. And the reason for that is because we are a small scientific community which is trying to do a moonshot project. And there is a similarly very small community among the chemists and life scientists who is doing their own moonshot project in the lab that's is reaching a tipping point at this point, and that is why they call it an origins of life project as opposed to astrobiology project. It is essentially building a chemical system which functions like a living cell, or a real protocell. And in a minute, I'll explain why this is important to our project. So these people are a small subset of what historically has been life scientists getting involved in exobiology and astrobiology since the 60s of last century. A lot of that early involvement, and to this day, was really based on interest of exploring mostly the solar system. And David Kathling's talk was a very nice example of how much this is useful to us as well. But there is a subset of those, mostly chemists, biochemists, and some life scientists who are attempting to do something else that is not necessarily to define the environment, planetary environment that sustains life, but the planetary environment that allows the self-assembly of molecules to the point of Darwinian evolution, and that hence that creation of a protocell. So it is important to separate those because they also have different projects in their own view. A lot of the earlier work on origins of life also reflects different environmental conditions and actually essentially different chemistry. Has to do most of what a lot of you are aware of deep hydrothermal vent kind of life origin, as well as sustaining it there. A lot of the new work that has especially flourished in the last several years and is, I believe, gone beyond what was accomplished before is really more of a surface phenomenon, which instead of being driven by mantle processes inside the planet is being driven by the irradiation from the sun. So in that sense, there are some very basic differences in the chemistry, but they also basically very different aspects of how planetary science and astronomy are intertwined in that work. And so that little subset of chemists who are working on the origins of life are then really motivated as well by the work that we are doing in their own words, as well as in what they actually are doing in these collaborations. Because to them, underlying assumption is that they will be able to recreate a chemical system that behaves like life if they follow constraints that come naturally from astrophysics and planetary science. So it is an iterative process between us and them to accomplish this. And hence the Harvard Origins of Life Initiative, which is now 10 years old, and the newer one, which you mentioned, which is a few years old as well.
So can we dream of us astronomers observing exoplanets, measuring conditions, handing those conditions to people that will go in the lab, build a tank, and reproduce these conditions and see if life pops up?
In a simple way, that's exactly what I'm explaining, except it's already happening. That is already with some of the scan data that we have of that parameter space of astroplanetary conditions, they have been able to constrain some of their pathways. And it is important to us because the rest of the life sciences community is huge and is watching this as spectators. And they are excited about what we're doing. I've given many talks to faculty meetings of that sort. But to them, what we are doing is not overlapping with what they are doing. And they're perfectly happy with that. The moment we announce something which we claim is life on Proxima b and have our own arguments why this is it, I expect that there will be a lot of people in that community which will question it. And unless we engage them now and educate them as well as we educate ourselves about their way of looking at the whole issue, I think it's prudent for us to start engaging them. So instead of inviting me to this panel, next time invite some of those people.
That's a perfect introduction to my first trick question for every one of you. What would it take? I'm going to start with Dave, and we're going to go this way. What would it take for you, Dave, to stand in front of a journalist with a straight face and announce to the whole world that we've got it, we found life on Proxima Centauri b?
Straight face. I mean, you know, I get the spirit of that question. I don't think I know the answer to that yet because we're still working out the theory, the theoretical underpinnings, and we're still working with the origins of life community to understand what it would take. So right now, I know what we should try to go and measure, but undoubtedly we will find some surprises, and then we will iterate with our theorist friends and our friends who work in geobiology and life sciences. So I hope that's not a cop-out, but I think if you look at the history of exoplanets, it's proceeded that way as well. If you look at the wisdom, in 1994, what the path of exoplanets was going to be, it was going to be that we should go and image Earths around G-type stars. And we just didn't predict the diversity that nature had in mind for us. So if I want to then say, well, what would it have taken, if you had asked me in 1994, what would it have taken for you to stand in front of a bunch of journalists and say, we understand planet formation? I think I could have given you an answer, but boy, that would have been naive of me. Because with all the intervening data, we certainly learned that planet formation is a lot more diverse than we had imagined, and it actually made us reconsider planet formation in the solar system, right? You can point to specific things that exoplanets have done to actually change our view of planet formation in the solar system, such as the importance of migration. So life being at least as complicated, forming life is, I hope, at least as complicated as forming a planet with gravity.
Probably is.
Chemistry. All I can say is to return to my point that I think that I can tell you now what gases we should look for and how we have to, hand in hand with that, characterize the planets in terms of their masses, radii, and insulation. But I can't tell you what the recipe will be to make that assertion in front of the press.
Lisa.
I think adding up to David, one of the things that we haven't finished doing yet, or not even really started, and this is one of the parts of the Carl Sagan Institute at Cornell, so we're trying to do a spectral database of forward modeling. What it just means is that you imagine a parameter space and then you see how the planet would present, how the spectrum would look like. Because so far we're taking Mars, Earth, and Venus and say every planet looks different. On every planetary environment looks different, and that's a very incredibly limited sample. So I expect a lot of this parameter space where planets will look the same but be very different because we can only access a certain part of the atmosphere. But I would say, what is the one that I would throw to our biologist colleagues and geologist comics and say, okay, and now tell me what the geology is that this actually is not. I can't explain this any other way than for there to be life. This is basically how I would put it. I would put journalists in a straight face, and this is our best guess for now, especially following David's lead. It's like we can say yes or no, but if you had a planet, temperate, right? So in the habitable zone, or you have the IR, so you know what the temperature is. You have ozone and methane, and you have an idea about the UV flux that hits the planet. I think I have a subset of models where I say, I have no other explanation for this. Go and find me a geological one that actually will blow this out of the water.
Okay. Nikole?
Well, to follow a little on with what Lisa said, I expect planets are going to be way more diverse than we could ever imagine. And I'm glad to hear that your group is doing this work where we can start to explore the whole parameter space of the sort of spectroscopic signatures that we'll see for these potential habitable worlds. And I think for me, having a planet where you have broad wavelength coverage and you're looking at all levels of the atmosphere and trying to understand all of those processes, and then being able to take something like this huge library of spectra and start to rule things out, photochemistry, geology, et cetera, you can get down to the 95, maybe the 99% confidence level that you just can't explain it any other way, then maybe I'd be comfortable. But that's going to be a huge amount of data and a huge amount of very multidisciplinary analysis.
So 95 confidence, not quite a straight face.
Yeah.
Michael?
Nothing. I mean, we've heard the answer in a sense, but from what David presented this morning about the stellar nucleosynthesis, the periodic table, geophysics and geochemistry telling us what can happen or what things can exist for more than 1 million years when brought in contact with each other. And all the complexities of planet formation, I mean, diversity is the watchword, and you ain't seen nothing yet, I suspect. I mean, we will find chemistries we had no idea what they were going to be.
Okay.
But straight face, who would have a straight face making that announcement? Not that they'd be smirking, but you'd be so overwhelmed with the possibility. I mean, it'll be exciting no matter what.
Okay. I have an idea of what Dimitar is going to say, but let's hear it.
Tell me afterwards. Well, actually, I think it's easy with one caveat. So the reason I think it's easy is because I believe biology will be different from planet to planet, but chemistry and physics will be the same anywhere in the galaxy. So as long as the caveat comes here, we are able to build that chemical system that behaves like life. In other words, I understand it because I can build it. then I will be able to make that argument only based on chemistry and physics. So just give me the data, and let's hope the origin of life works, then we're done.
But I'll give you a spectrum.
Yeah, a spectrum.
Okay.
I'll be able to interpret it based on what I understand, which I cannot do today, but in 2 years, we should talk again.
All you'll know is how far out of equilibrium it is and what's
could
in
be,
there.
Yeah.
Okay.
David said how you put the whole system. The only part which we need in that system is the data that you're going to give us, or all of us are going to give us, and an understanding of what to anticipate, which is we don't have now because we don't have a working protocell.
Last trick question, very quickly before we invite the audience to ask their trick questions. If you had the opportunity to pick an instrument that you would put on the starship, what would it be, Dave? It's heading to Proxima Centauri. You have one ground
a
allocation.
life finder instrument, obviously. No, I mean, neat things that you could do that are hard to imagine doing from afar would be to measure the magnetic field of the planet. And you know, if there was some way to, I mean, that's at odds with the small nature of the spacecraft. But you know, certainly a resolved imaging would be tremendously exciting.
Lisa?
I think I would go for a high-resolution spectroscopy because you'd be there, and so you could actually have these additional beautiful things of, you know, surfaces, atmospheres, and I'd go with that. Like, you know, filters. I think that's what we were talked about last time. Like, do use a camera and do use filters, but, you know, if I can pick high-resolution spectroscopy and something to send me back the data, all of it, please. Not just a yes or no, Avi.
Avi is taking notes. Nikole?
Yeah, I'd go the spectroscopic route, but I might go for lower resolution, broader wavelength coverage.
You said we can do anything,
Anything
so
we want.
high resolution, all wavelengths.
Spin it down as much as you want, sure.
But yes, I agree with you.
Yes.
Michael?
A real estate agent? I'm not sure. That's. No, yeah, apart from the other answers, I'm not sure what I would like to be able to assess the thermal emission and the reflected light so that I could try to get at greenhouse.
Okay, so I however, have a precondition. I want at least 10 chips, not just one. So then, 2 of them, I'll point at the planet, straight in the planet, hit the planet, and create a thermal event in the atmosphere, and use the other 8 to do exactly what our colleagues told us and beam the data back, because you'll get a lot better characterization of what's in the atmosphere.
I'm picturing Independence Day.
Okay, so that's good. We've got 14 starships already claimed for, yes. So now it's time for the audience to ask questions. It will be my great pleasure to throw microphones at you. So if you raise your hand, be aware
Watch your coffee.
that a high-speed projectile is heading your way, and you need to catch it, and you'll speak to it. And you can throw it to the next person.
All right. So we've been talking about nearby M dwarfs a lot. From the 7 nearest things to the sun, 3 of them have gotten almost no mention or no mention. That's Lumen 16A, Lumen 16B, and WISE 0855. Presumably because they're brown dwarfs, they're very faint, they don't have a lot of emission in the optical or the near infrared. But this is breakthrough, and we are talking about the nearest objects. So how interesting are these objects, aside from the fact that they're very hard to study right now?
Dave, are you looking at them?
No, because I just don't know how to find planets around them from the point of view of rate of velocities or transits. There's no question that they'd be very interesting, and surely they'll be eager targets for high contrast ratio imaging. But you know, to get rate of velocities, I mean, we're doing all we can to build exciting. There's exciting spectrographs being built that are focused on M dwarfs, but not on brown dwarfs.
What if you did a transit mission in a near-infrared?
That would be poor design because you know the transit probability, so you would never say, well, with 3 I would expect to find something. That would be a miracle.
You could look at more than 3.
No, you're talking specifically about these 3.
Astrometry may be easier.
No. Listen, the idea of doing a transit survey of nearby brown dwarfs, that's a great idea. Somebody should do that. Oh, they did. and they found 7 planets. So, you know, if I just don't know if TRAPPIST can get there, or if these guys are even fainter. Because these ones, you know, TRAPPIST-1, the star, is like clinging to the main sequence with a fingernail, right? But these things that are actually brown dwarfs and are fading away, I think they just get faint awfully quick.
Just so if I can chime in, I mean, this is something that people have been proposing to Spitzer actually for quite a while. I've been on several of these proposals because obviously you'd have a very short period habitable zone, and Spitzer would be ideal at 4.5 microns to just sit and stare and look for transits if it had nothing better to do.
I'll just mention that these faint primaries are perfect direct imaging hunting ground for JWST in the sense that you're not contrast limited, or at least where the background limit and the contrast limit meet for the very faint primaries. It's the perfect thing to do. And for things brighter than, you know, even 7th magnitude in the near infrared, you're better off doing it from the ground where you'll be contrast limited. But for JWST in the background limit, we're not talking about detecting a habitable planet or one Earth radius planet, but there'll be amazing direct imaging surveys on very faint primaries like those that are very close.
So I guess this question is for Dimitar. How would you convert the comment, and some people believe that life didn't have its origin here on Earth, into a scientific question? And is what you're doing now going to have the capability of answering that question? Is it possible that life didn't originate here?
Yeah, that's a valid question. And actually, I believe that the future of life populating the future galaxies in exchange rather than chemical transformation, because it's much more efficient, but you need many Hubble times in the future for this to start working. But as we look at it currently with the short-lived universe we live in, the more likely scenario is that most of the planets that we'll see life on are also the locations where it emerged from the planetary conditions, or at least in systems like the TRAPPIST-1 system, where there are more than one in close orbits to each other. It was local transfer of you know, the material from one to another locally, which to me doesn't change the equation very much, because you have the same star, you have more or less the same conditions, just slightly different orbits. So from the point of view of the chemistry of emergence and the chemistry of initial conditions, that's a much more restricted set. If you're thinking, indeed, I understood your question about real panspermia, which is exchange between stars, stellar systems, then I'm with Jay Melosh and the estimates from many years ago, where this is just takes too long and it's too far of a journey, and the probability is currently in the current universe too small.
That answer does not factor in the possibility that it's intelligent.
That's correct, but I think our chips will be very well sterilized by the time they reach Proxima, don't they? Especially if they hit the atmosphere. It's a little nuclear blast. So.
I see questions behind you if you're just curious about where to throw the box next.
Oh, he's cheating. Oh.
How strongly would you prioritize searches for life elsewhere in the solar system, you know, Enceladus, Europa and all that? Because if we find life there, that immediately says it's going to be widespread, which would answer one of the most important questions. So are there feasible things you prioritize in our solar system?
That's probably a question for Dimitar.
I would, Martin, I assume that's you by your voice. I couldn't see you here. I'm a big supporter of those explorations. I just think that our administrators should not take money from one and put it into the others. They should be both done, and it's not a zero-sum game. I think it has a value from many points of view, including knowing our backyard. And it has a value even if we don't detect anything, because that narrows the parameter space, which we can say, well, this looked like a chemical planetary environment where life should have self-assembled from chemistry, but it didn't. That's very helpful as well. So if I knew for sure that Enceladus and Europa had no life on them, that is going to help me immediately in some of this chemical pathway work. John Sutherland, for example, will argue that.
You never really have the negative, but the positive is already hugely important, isn't it? Because
oh, well, there is no question.
Life would be
there is no question. Especially if we have it here in the solar system, we can study it in molecular detail, which is
different hands.
There is no question about it.
So I'm curious. I'm gonna break the rule and ask a question. What would you bet that we will find life in the solar system?
I'm almost ready to give up on Mars because the initial conditions on Mars look like what would have worked on Earth, and then the sheer speed with which a chemical system like that adapts means that life should have survived today in some form or fashion. And the fact that it's not really easy for us to detect any signatures on the surface. I know people are talking about deep inside the crust, but Freeman Dyson once said, you know, life is a system which cannot just stay still. It will, one way or the other, reach the surface as well. I'm ready to give up on Mars. I'm still not sure what to think about the cases of Europa and Enceladus, because yes, the water is there, the right temperature is there, the minerals are there, but if indeed most of the pathways that now appear very promising require UV irradiation directly into the water aquifer, that's not there. Titan is a completely different ball of soup, or how do you call it in English?
I thought you were going to say
fish? I'm not sure
I'd love to see Titan explored simply because of the chemistry. And if something is actually happening there, that will be fascinating, because that will be life as we don't know it for sure. So what can I say? I think it is a very exciting possibility, but I would say it's less than 50-50 chance that we'll find anything.
I think one thing to add to this, and I completely agree with Dimitar, but one thing to add to this, if we were to find life on Enceladus or Europa, especially if we found it by just going, for example, through the plumes or not having any option to have contaminated it, what would change for me significantly is that now I can actually make the assumption that as long as I have a body of water, I can start life and then do the stellar evolution. The temperature is nice and warm, and basically, we're not considering frozen over planets around other alien suns, not because we don't think there's life, just because the ice on the top will basically keep gases from easily escaping into atmosphere where I can see them with my telescope. However, if I found life on Europa or Enceladus, that would basically tell me that it's a waiting game, right? So I could actually say, okay, this could have started on a frozen surface or subsurface, and it would, for me, actually, I think for everybody, change our perception. If we had a second point where life is in our solar system, that just means it has to be everywhere. And I think what Martin was getting to, if we don't have one, that means in our system it was just once.
Who has the box? You can throw it to any raised hand. Yeah, thanks.
We've recently heard of time domain phenomena that are hard to explain from natural causes, and some have interpreted as signs of intelligent life. Is there any non-intelligent life biosignatures that manifest in the time domain that we should be thinking about looking for?
Non-intelligent.
Well, listen is listening.
But you're saying non-intelligent life, so some phenomenon that life does that doesn't, it's not an intent to communicate.
Well, Lisa mentioned this secondary emission, right? This idea of...
Right, or one other thing you could think about, and maybe even easier, is like if you had something like an algae bloom, right? That were maybe induced by UV or maybe a seasonal thing. So we are looking at, or we are considering these things. The only problem is that you can also envision so you have to make sure that you know what you're seeing, whether it's a surface feature or not a surface feature. This is why we're being very careful. We've, for example, made a color catalog of life, and sits in the audience if you want to know something about it, trying to constrain what is life or what can be a life feature, even temporary, versus non-life. I think what you're talking about is something that wouldn't be that will be linked to some natural phenomenon, whether it's like a pressure of food or a seasonal pressure. So our hope would be that you could actually link that to seasons or to stellar activity, and therefore actually have and it should be, if it's life, it should have evolved for it. Therefore, you have the potential that it's actually a much bigger signal than any non-life signal that wouldn't have had Darwinian pressure to actually go for this. I think short answer is we're keeping our eyes open, but so far we haven't identified anything except for something like, we're starting to explore something like biofluorescence or anything like that, to make sure that temporal signatures that could indicate life and even non-intelligent life.
I mean, I can think of a few just in analogy to the Earth, right? If you could imagine studying the CO2 abundance in the atmosphere, and you did that for the Earth, you would see the annual cycle just due to the greening of our continents as the chemical exchange with the atmosphere happens with life on the surface, and maybe that would be a way of inferring from CO2, which itself is not a biosignature gas, that nonetheless there was life there. And there's many, many things that of course change throughout the seasons on the Earth that could be in principle remotely accessible. So any of those are great things to think about.
I think the key point is to make sure that we have no other explanation than life for it. I think that's really where we have the missing information. It's not that we can't come up with something that life would create that we should be looking for. Like, for example, CO2 is made by life, but it's also made by lots of other stuff. Methane alone is made by life, but it's also made by lots of other stuff. So making it a unique signature is where we have a lot of work to do.
Burden of proof is tricky.
Burden of proof, yeah.
So this was hinted at when you were talking about Mars, but isn't focusing on the chemistry of the origin of life a little restrictive? Because it could form in a rarer environment, then quickly adapt to the dominant environment on the planet.
That's the point. We want more restrictions rather than everything goes. So yes, it is more restrictive. The set of environments which allows for the chemistry to happen appears to be more restrictive than the set of environments which allows life to sustain itself. But that's also a statement based on the assumption which we understand adaptability or Darwinian evolution like adaptability of the life as a chemical system, which we don't. Until we have a system that we can play with and see it actually evolve those adaptive properties, we only assume that it's similar to what we know from the history of life on Earth, which is pretty well documented, but it's just one example.
I think one point that you're making that's very well taken, we take this into account in our consideration, is like a planet is not one thing. It's not one surface temperature, it's not one thing. And especially if you do subsurface, like an ocean or anything else, you could have a small pocket of water somewhere. If that's enough to get life started, it might be able to adapt. And I completely agree with you. But the question still is, maybe there are some conditions where those are so bad that you wouldn't find life. And that's what we're trying to also figure out, because we want to constrain our data set in a way. As I say, anything goes, but hopefully we constrain it a little bit more. And for example, temperature is one, right? Our temperature or UV, at one UV thing, everything breaks down that we know, right? And we have no protection where if you hit something with enough UV, then it's dead. The cells disintegrate. That's, for example, one limit, but the other limits are up for grabs.
We heard this morning that if we look at Earth in the past, it doesn't look the same as it is now. Should we be worried about maybe we're going to look at a planet and we're going to catch it during the Snowball Earth episode, for example, and we're going to say, oh, that's not a habitable planet, we're going to move on? And it seems very risky, actually, in some sense. What are your thoughts on that?
I think, can I maybe just chime in for the snowball? So we know what our Earth went through, so I think we wouldn't say it's not habitable. We would just say this looks like a frozen over place, where currently, because the ice coverage is going to block in the gases anything produces, I won't be able to see anything. However, I think this is also the borders, the cases that we can actually use to bracket, because I think a lot of things we will see is like, oh, this looks like an early Earth. But it could also be a completely lifeless body, because I don't know what makes the CO2. So 2 billion years from now, let's go back and have a look.
This goes back a little bit to your question about the straight face. So basically, it will be probably prudent to have enough statistics to make these conclusions. In other words, to have a gallery of a sample of planets which you have studied, and for some of them you see geophysical evidence for one particular episode, which is a time-dependent thing, and you build up the case for those which show the biosignatures in the proper context. And so the question then is, how many of those do we need? Do we need 3? Do we need 10? Do we need 500? And there is still no agreement in the community what is a prudent number there, but it's certainly not 1.
I mean, for me, the big picture is not the statement that in the next few years we're going to, for the first time in human history, have the sensitivity to look for life. Okay, because that's something we argue about. It's the technological ability to study the atmospheres and the surface conditions on terrestrial temperate planets. That's a specific thing. For the first time in human history, we're going to be able to look at rocky planets orbiting other stars that have the same temperature as the Earth and determine the molecular abundances and the temperatures of those atmospheres directly. And that seems to me like, you know, that may open up the detection of life, but it will just provide an infinite set of possibilities in terms of what we will learn and ultimately put the Earth in context. And so it's that technological door opening that will just unleash this flood. I don't really know what direction it's going to go into. I honestly don't want to get too caught up in terms of like what exact molecules. They all have sort of the same, I mean, once you get down to the signal, it's basically the same drivers, right? How big is the atmosphere? How far away are these planets going to be? We know the answers to all those questions now. So we know what the answer is. And what's amazing is, you know, a 6.5 meter infrared sensitive telescope in space is really profoundly different than a 2.5 meter telescope in space.
I would just
say a 25 meter or larger telescope on the ground is profoundly different than an 8 meter telescope on the ground. And so we're going to move from studying the atmospheres of gas giants, which we've done with those smaller facilities, studying the atmospheres of Earth-like planets. Maybe that gets us to life, maybe it doesn't.
I would just add, don't forget about temperatures that aren't quite as temperate as you would like on edges. Let's just be open to larger possibilities.
Right. I say temperate, not habitable, because nature wouldn't let us use the word habitable anymore in our paper. They said, we don't want to use that word anymore. Say temperate. And we say, OK, that's fine. Temperate's good.
So we have 2 microphones in place, so we're going to alternate one and then the other. So let's go with Avi, and then he's going to go the other microphone. And then, Avi, when you're done, you throw it, et cetera, et cetera.
We've been focusing in the discussion mostly about the composition of atmospheres. And I just wanted to bring up another aspect, which is on the interface between the search for primitive life and the search for intelligent life that we will hear about in the next session. And that is the possibility that we will find the surface of a planet or the atmosphere of a planet to contain ingredients that are completely unusual. For example, if a planet is being terraformed by intelligent beings, it might have surface conditions. For example, if there is a tidally locked planet that has a day side and a night side, power from the day side will be transferred to the night side. And by observations, you can tell if one side is dark or it's illuminated artificially. Another possibility is there would be molecules in the atmosphere that you cannot make, you just cannot make naturally, that are artificial in origin. So I just wanted to hear your views about the prospects of finding signatures that are not in terms of looking for oxygen, but in the data on the surface conditions and the atmospheric conditions that would be completely out of sync with what we might expect geologically.
That goes back to the question about what is a prudent sample size. And my sense is you will more likely discover something like that with a larger sample size. On the other hand, if you're already at the level at which you can see this kind of artificial molecules and illumination, breakthrough listen is probably going to detect some radio signals from that before that. So there will be a correlation in that 2 samples, you know, between the 2. Of course, but you know, there are all these possibilities to correlate the samples as long as you can have a big sample. If your sample is small, then that's more.
I think one of the things people have looked at for a long time is things like freons, right? So, or any man-made gases. The problem is they are trace gases in our atmosphere, and they might actually be an anti-biosignature if you have enough of it in another atmosphere, because that means they killed their ozone layer and didn't stop it, right? So it's a question. However, for the amounts we would make, or we could possibly think another civilization would make for atmospheric gases that are technology made, you need a breakthrough thing to fly by to be able to do it. It has to be in your solar system, or you need a telescope that's even by a factor of 10 bigger, because it's such a small signature. For example, freons are at 17 microns, so an infrared one would give it to you if you had the sensitivity. However, other things that we looked into, or what in my team we're looking into, is trying to figure out, what about if a civilization, and this is again a breakthrough thing more, is like just annihilated itself? You know, that would be like something like a nuclear winter. You know, you would see that, right? Whether or not you could actually say it's nuclear winter versus it's a huge volcano thing is an open question, because then it comes down to the resolution. Could you tell one kind of haze apart from another haze? And so far we don't think so, because we don't have the data. But there are things that we're thinking about. However, man-made gases are usually luckily, in incredibly small amounts. And if you had a planet that were terraformed, right? The question is if you could tell that apart from geological effects, because you would try to mimic some geological effect to make it terraforming. So I think it's a fascinating question, but it's completely open. The only thing we could do is light, as you had in your paper, but I think the problem was there too, that they would have to have an amazing amount of light on the night side for us to be able to tell any difference.
And that would be really bad for the astronomers who live on the night side.
We wouldn't have any astronomers.
I hope this is not what we're going to see.
Can I just interject quickly? I want to bring back the sample size again, and I want everyone to keep it in their minds, because I feel like a lot of us go into these large-scale observatories, and people always underscope what they need to answer a question, and we can't really do that. And then, you know, we need to actually scope the sample size that we need, say, with JWST, to start to make headway in answering some of these questions.
I think it comes back to, some people have asked me, it's like, so once you found the first Earth, what's next? I'm like, it's the second one, it's the third, you know, so we actually start to understand what we're seeing. But I think it's a very valid point.
And remember, we got about 200 billion stars to sample, so it's not going to stop tomorrow. Where is the other blue thingy?
No, there's two.
Yes. Yeah, so Avi just stole my question, so I'm going to have to come up with an advert for my own work instead. So Lisa, you kind of touched on some of the things that myself and Jack, your postdoc, actually worked on the paper a few years ago about what happens when you look for dead civilizations. I think I would just tack on the fact that, yes, obviously if there's a huge amount of pollution in the atmosphere, or they've done something really quite significantly bad to the star, like dumping nuclear waste in it, is a sign of something bad. And it might well be an indication that the civilization is dead. But that gives us information in the same way that if we went to Enceladus and found no signs of life, that is also a data point. And it's a data point more about what happens to our future. And it's a huge piece of context to say, well, okay, we can find one more example of intelligent life that was short-lived and made stupid decisions. Are we going to be the same? So that's just one extra thing to add on, seeing as I couldn't ask the question, because Avi had asked it already.
I think one of the other interesting things is that what we're marrying, right, is like, yes, you might have destroyed the intelligent life, but you know, wiping life from a planet is so incredibly hard. And even if we all die, the cockroaches, tardigrades, they'll be super happy and fine, right? So I think this is also the interesting thing where we're trying to find markers for life as we know it. And then there's a lot of stuff that we can't even anticipate. So we're looking for things we can't explain.
The only thing harder than proving there is life is to prove there isn't life on a planet.
Yeah. I don't think that's actually doable.
No, yeah, that's not doable. Right?
So yeah, my question, I guess, touches on this issue of sample size. And there is a technique in statistics called hierarchical Bayesian modeling, which is optimized for thinking about samples and populations. But it really means that we have to let go of the question of, does that planet have life on it? What is the probability of that planet having life on it even? And really we're asking, what is the frequency of life? And that should be a question that we're kind of familiar to thinking about with Kepler, because that's, of course, what it was trying to answer, was the frequency of Earth-like planets. So it's a statistical language to maybe ask this question. And I think it's relevant because it does affect the design of your survey. I know, so from my experience looking for exomoons, that was always the way we tried to tackle it from a statistical perspective, not a fishing expedition. And it does affect the way you design it. And I just want to add, if we want a completely unambiguous detection of life, what else is there apart from SETI? I don't know how you feel about that, but I feel like that's kind of the only way to have like this sequence of prime numbers or something like, okay, yeah, sure, that's a definite signature. But it's unclear to me whether we could ever have that straight-face situation realistically, apart from with a frequency.
Wouldn't you try to characterize chemical diversity and put a framework in place to do that, and then use those techniques to optimize the survey to span that space and perhaps constrain this equilibria?
Yeah, sure, yeah.
As opposed to looking for life.
Yeah, I think there you're just really describing what type of forward model you use.
Right. So you eventually, if you're lucky, you do both.
Yeah. But I mean, I definitely didn't want to convey that I think this can't be done. I think it will be possible, based on things we can measure from afar with telescopes, to infer that there's life on another planet. What I was trying to convey is we don't yet know exactly what that will take. We have developed enormously in terms of our understanding, not just from astronomy, but from studies of the Earth throughout its history and through origins of life work, as to what we now think it'll take, but that will go hand in hand with getting better data of the atmospheres of those planets. So I think it is possible. I just can't currently write it all down. I don't think SETI is the only conclusive answer. That would definitely not be my view. I think SETI just provides a different path for a very specific question, which is intelligent life. But perhaps there is a universe teeming with life that's not interested in communicating with us. It would be a shame to miss that.
I think the other question that you might want to ask in that context is, I agree, if you looking for radio signal, optical signals, you actually constraining the amount of time. If you have the life on the Earth 24 hours, like the 4.6 billion years, then life started at 3 o'clock in the morning, but it started to use communication and radio waves a couple of seconds before midnight or a second before midnight, right? So you're losing this whole context of where life was there, but it didn't actually communicate via radio waves. And I think it's not just a search for life while we're doing this. We're really trying to do the context and also understand our own planet better. And we have one data point for Earth's evolution and for the evolution of life. We want a couple more, and whether it's gone to the intelligent life route or not, or to the radio route or not, or optical route. One of the things that one of my students said is like, what about if you have an ocean world with whales? I'm like, yeah, that's going to be, for example, that will probably never go into a SETI direction. However, it can have gases that we look for and so on and so forth. So I completely agree. I think it's a very complementary approach, but it's a very specific small window of time currently that we're looking for communicating signals versus a whole parameter space of life that probably is out there in different kind of evolutionary stages that would tell us a lot about evolution of a planet and life in the first place.
I'd like to bring up actually, we've done a lot of work with brown dwarfs and hot Jupiters, and they have shown us that, our understanding of gas giant planets from the context of our solar system was way too narrow. So a lot of these same techniques can be applied to a lot of the sort of characterization work that we're doing now for the gas giant planets, and then extended to help us better understand how to do it for the terrestrials.
So I apologize for those who are holding the blue square, but our time is up. Okay. This was great. I'm sad we have to finish so soon. Let's thank our panelists. Thank you. And I think we have a break, right? I should be aware of the schedule. Thank you, everyone.